the Hitex webinar series about Safety and Security Suite, SafeTpal. I'm Michael Weiss, I'm Senior Account Manager at Hitex. In today's webinar, we will explore seamless development with MathWorks Hardware Support Package. I'm particularly looking forward for the live demonstration that will be present later in this webinar by my colleague Aranian. He holds master degree in embedded system development and has worked in the automotive industry for over 8 years now. On the other hand, it's me, Michael Weiss. I'm Senior Account Manager at Hitex since about 10 years. We'll all work for Hitex. Hitex was established in 1976 as an embedded development company and has achieved rapid growth by developing and providing microcontroller tools. Today, Hitex, as a proven expert, is also in great demand as a service provider for training and consulting, test services, development and production services. Our commitment to quality ensures that our customers receive world-class service with the focus on safety and security. Hitex supports all phases of your project from the idea to the finished system. And now we will start with the webinar. SafeTpal is a suite for ease of use for AURIX development with TC3 and TC4 microcontrollers. We address a special focus for all the companies who need a very good solution, and we help the companies with SafeTpal to reach their goals in the project. So what is SafeTpal? It's a complete safety suite for safety and security. SafeTpal is a complete ease-of-use solution for the AURIX TC3xx and TC4xx microcontroller family for high-performance applications which use non-AUTOSAR or AUTOSAR as the runtime environment. On the other hand, we support standards. SafeTpal is designed for all applications up to safety standards ISO 26262 ASIL-D and IEC 61508 SIL3 and security standards like ISO 21434, CERT-C and MISRA-C. SafeTpal is a complete package consisting out of software, hardware reference design, services and trainings. Because in the V model, SafeTpal gives you a lot of services, and as you see in the lower right, now we are focusing on SafeThsp. Okay, it's your turn, Aranian, please start.
Good morning, everyone, and a warm welcome from my side for today's webinar participants. First of all, thanks for the brief introduction, Michael. I really appreciate the fact that you have set up the stage for me to take over from here so that I can get started with the most important topic of our today's webinar, which is on MathWorks HSP. And of course, I would shortly highlight the fact where our SafeThsp package from SafeTpal offers its value proportion in terms of model-based development workflow. Before we get into the nitty-gritty stuff, let me shortly introduce myself in short. My name is Ranyan, and I'm the FAE here at Hitex. I take care of all the pre-sales related technical topics, and I'm usually the first point of reference for our customer whenever it comes to technical clarification on Hitex products. Also, please feel free to drop your questions, as Michael mentioned, on chat. We'd be happy to pick them up by the end of the webinar and try to address them. So for today's webinar, I'm pretty excited to walk you through MathWorks HSP package and also our SafeThsp solution from Hitex, which I feel is a unique value proposition from Hitex SafeTpal product offerings. So to keep this simple, I can say that SafeThsp is a software package that would be helpful for developing your proof of concepts with MathWorks hardware support package, and of course in conjunction with the Infineon's AURIX TC3 and TC4 microcontrollers. We'd also like to show you how SafeThsp enables a safe model-based development workflow, say starting from simulation step to a production-ready stage. And irrespective of your application, whether you're developing software for automotive ECUs or motor control applications, or even for power conversion systems, our SafeTpal and SafeThsp solution from Hitex will help you accelerate the development while staying within the safety compliance frameworks. So maybe let's get started. First slide, let's dive deeper into the architectural view of SafeThsp and SafeThsp drivers. At the very top on this slide, what we see is our application world. Let's say it's where the Simulink or customer application is potentially running on a Simulink state machine or on your favorite OS like PS-ROS or SafeRTOS. And this is where your algorithms and control logic are running. Below that, we have the essential foundational elements like DMA, interrupts, and trap handlers, and of course also the boot manager lying in parallel. Now, maybe let's look into the most important red box down there. This is where the hardware software package from Hitex is being offered, and it's also part of our SafeTpal offering. This block denotes our Hitex base software modules, which includes our well-known safety pack solution that has been already well deployed and very well adopted by a lot of customers for implementing the assumptions of use cases and ESMs with AURIX TC3. In parallel to that safety pack lies our SafeThsp and safety hall modules. As you can see here, safety hall basically stands for the safe hardware abstraction layer. Think of safety hall as your highly qualified or robust driver for low-level MCU hardware peripherals. And of course, it provides safe access to all those critical AURIX peripherals, which we basically rely on for our development and for our applications, especially say your EVADC, QSPI, DMA, UART, SPI, and also the powerful GTM and many more of such hardware peripherals would be accessible with our safety hall driver. And building directly on top of safety hall, you see then our SafeThsp solution. This is our safe hardware support package for model-based development workflow. This is where we elevate the abstraction even further by providing high-level services and integrating crucial safety mechanisms between the hall layer and the application layer. Just to be precise and keep it short, I would say that SafeThsp functions as an ILD wrapper and is completely compatible with applications using the high-level APIs from ILD. All right. Let's talk about how you bring your ideas to life on the AURIX chip. The slide here shows you the typical workflow, especially when you're working with MathWorks tools and model-based development workflow. At first, it all starts with the function modeling. This is where we build a virtual version or say a block diagram of your system. We build this function model block by block, integrating each one of these blocks together and then resolving the interdependency between each one of the blocks. So as a next step, we make sure that we use the hardware support package for AURIX from MathWorks and be able to use all the HSP blocks, say for example, the EVADC block or the PWM block that can be picked and placed on your console, and then followed by connecting the HSP blocks together with the function model, which we developed in the earlier stage. And of course, we'll be able to also configure the HSP blocks based on the use case and application. And if we look into the next step, then comes the interesting part. So once our model is behaving perfectly up to this stage, then the workflow continues with automatic code generation with the help of the embedded coder plugin from MATLAB, which takes in our Simulink model and automatically creates a high-level optimized C code. And there is no more manual or error-prone coding from scratch, as it's optimized C code and which is automatically generated. So this code will also be, of course, tailor-made for your AURIX microcontroller. And last but not least, after generating the code, we move into the build phase. This is where your generated C code along with other software components gets compiled, linked, and we flash this generated code onto the AURIX. And this is where the compiled program is loaded and is flashed directly onto your physical AURIX microcontroller. Finally, then we hit the testing and verification stage on the actual hardware itself, where we will run target application on the AURIX itself, where we perform real-time tests and also use measurement tools to see how your system behaves. Not to forget, there is usually a feedback loop between the stages, which is super important because it helps you refine your model on a step-by-step basis and make sure that everything works perfectly in the real world. So long story short, what's the key message here? This workflow means that you design visually and also generate code automatically and be able to flash it onto the chips and then test them thoroughly. Moving to the next slide. Um, Typically, MathWorks HSP provides a Simulink block set that maps Infineon's ILLDs. When I mean ILLDs, these are the Infineon low-level drivers for AURIX TC3 and TC4 microcontrollers. For example, all these block in the slide are a perfect way for getting started, but they are not meant for safety-related production systems at the moment, especially as they are using the ILLDs at the back end. I can already say that all these blocks will be included as part of the safety HSP framework from SafeTpal. So you always have a wide portfolio of functional blocks to choose, and you have the complete flexibility that you had also earlier with the ILLDs. What we have also done with Safety HSP and Safety Hall is that we introduced a driver stack that provides the same API set as ILDs. So your model don't need to change, but under the hood, you are using the qualified software, which is proven and production ready for such an use case. And now here how Safety HSP addresses the issue that we were discussing all throughout this webinar. As you can see here, the existing model-based development framework makes use of the MathWorks HSP package, which is fundamentally built on top of the unqualified ILDs from Infineon. Of course, MathWorks HSP package doesn't cover all the ILD packages, but whatever is important and useful within the scope of an model-based development workflow is taken into consideration. These ILDs actually sit between the hardware and the application layer of the Simulink model. Therefore, it directly interacts with the low-level hardware peripherals. And on the other hand, say on the other side, they would also be able to interact with the application layer with the Simulink's APIs or ports. So you might be wondering, where is the value proportion from Hitex on this workflow? Traditionally, you'd be using these ILD drivers within such a workflow. And as I mentioned, although these ILDs are an excellent choice for prototyping, they have this downside that they are basically unqualified. This often means that we would have to completely rewrite or at least take significant efforts for integrating and verifying new set of drivers, especially when you move from a proof of concept phase to a production ready phase in your safety critical product. So Safety Hall and Safety HSP together changes this perception of using unqualified drivers in a model-based environment. So what does it does under the hood? They directly replaces those unqualified ILD drivers with the qualified production-ready components. This means that you are developing applications right from the start with a rock-solid driver, even from the proof of concept phase. And you also ensure that you need not anymore switch drivers in the mid of your project or by the end of the day for such production ready use cases. Once again, the key issue here is that the ILDs are unqualified. Our core approach is to replace this pain point of ILDs with our Safety Hall and Safety HSP solution. As you can see here, this is where the Safety HSP and safety blocks are positioned in the model-based development workflow. We provide those qualified Safety Hall drivers, which are specifically developed and tested and also qualified to handle all your critical hardware interactions, which includes all those essential drivers and components like your EV-ADAC for precise measurements or PWM for motor control, and even the fundamental port drivers for managing your IO pins can be covered with the Safety Hall driver package. Also, on the other hand, Safety HSP in this case functions as an ILD wrapper. What do I mean when I mention ILD wrapper for this workflow? It basically means Safety HSP can encapsulate and manage all the existing ILD calls, which makes our solution adaptable and ensures a smooth integration within our existing workflow, so that you don't have to throw everything out. Instead, you enhance your current setup with a qualified safety layer on top. And in essence, I would say that Hitex Safety HSP and Safety Hall or your trusted partners in model-based development, which bridges the gap between rapid prototyping and safety-critical, production-ready AURIX projects. Imagine right from day one using such drivers that are built for safety and reliability gives you the leading advantage in the market, and make sure you bring your products yearly on with time to market. So before we get into the interesting part of today's webinar, which would be a live demonstration with MathWorks HSP package, long story short, let's try to summarize what we offer from Hitex side on the software package of SafeTpal. If you're trying to analyze a broader picture of model-based development, especially in safety-relevant applications, many of our customers heavily rely on MathWorks model-based development flow, especially using Simulink and embedded coder to build control logic and deploy it directly onto the AURIX hardware, which I just explained. Excuse me. However, the default drivers underneath these blocks are typically Infineon ILDs, as I mentioned, which are great for prototyping, but they are not qualified for use in production-ready safety-critical systems. That's where SafeThsp comes in. It allows you to continue using the same HSP block interface in your model, but replacing the underlying drivers with qualified SafeThsp drivers, which means you basically eliminate the need to redo or reintegrate your application logic just because you moved into a safety critical project with safety constraints. On top of that, we provide Safety Hall, which acts as an hardware abstraction layer. It also mirrors the ILLD APIs and configuration structures, but does it in a way that it is qualifiable. And in essence, Safety Hall bridges the gap between the unqualified ILLDs and choosing between a highly formalized ODOSA MCAL stack. Last but not least, SafeThsp currently supports AURIX TC3 device, and we'll also be actively working on supporting it for TC4 as well in the near future. These SafeThsp blocks are fully integrated into MathWorks HSP framework, so that you can use them right away with your existing model-based development workflow. Yeah, now it's also important to note that if you are using ILLDs through HSP, there is no safety process applied to those drivers by default, especially if you are aiming for functional safety compliance, say ISO 26262. You need to go through MathWorks IC Cert kit and related tool qualification process and guidance needed for such qualification. With SafeThsp and Safety Hall in place, you get a pre-qualified solution that significantly reduces the burden on your team. One step further, so great, so far so good, and I think it's time to jump into the exciting part of today's webinar, which would be a live demonstration with the MathWorks HSP package, and of course with an AURIX TC3xx light kit. Before we get started, here's a slide to let you know what we will do on the second half of today's webinar. To start with, there is some basic software installation and setup that's needed to be done. Make sure that you have the most recent version of MATLAB installed, and also the Hitex compiler installed on your machine. Also, make sure that you have downloaded the ILDs, which are the fundamental blocks of the MathWorks hardware support package. And last but not least, make sure that you have a logic analyzer like a picoscope or Saline analyzer for scoping through the signals from the pin headers on the board. And here's how I'd like to break it down for the demo session. At first, we'll create a Simulink functional model and run a model in the loop simulation to make sure the logic works as expected. Followed by that, we'll configure the hardware to set up clocks and the communication interface on the board. And then the third step, we will run a processor and loop simulation to test the real-time behavior of the controller running on the actual AURIX chip. And finally, we will connect the peripherals in the module, generate code and deploy it, and see it running live on the board to see what happens. Just to give a feeling, in this demo, we are going to control the brightness of the LED on the AURIX TC3xx light kit board just by turning the potentiometer knob, which is on board. So it's a simple example. However, I see this as a very good example to show you guys how to go from a Simulink model all the way to real-time hardware execution using MathWorks HSP blocks. Specifically, we are using the AVADC block to read the analog voltage from the potentiometer, and then we use the PWM block to control the LED brightness via duty cycle modulation, which happens at the core of the AURIX controller. And as you turn to the potentiometer, you'll also see the LED brightness changing in real time. I think, as I told, it's the most simplest way to demonstrate end-to-end model-based developments with ILDs. And as I mentioned earlier, I'll be using AURIX TC3xx light kit for today's demonstration, but always remember that SafeThsp package itself will support a wide range of TC3 and TC4 dev boards in the future. Here's how the physical setup of the AURIX TC3xx light kit would look like. So you can see a potentiometer mounted on the board and the LEDs right next to it. The USB interface connects to the development host, which is your netbook in this case. Actually, the notebook in this case. The analog pin to scope would be the fourth pin from the bottom, and the output PWM pulse will be on P005 pin header. As mentioned earlier, you would also need a logic analyzer to scope onto this pin. And as you can see here, the setup is simple and straightforward for validating plant controller interaction, especially if you want to show how fast the system responds to analog changes. So first things first, what are the stages that are typically included in a model-based design? So if you look into the core stages of model-based design, we progress through a series of so-called the in-loop test, each one bringing us closer to the final hardware. I mean, running the simulation on the final hardware. Say we begin with the model in the loop test, where everything is simulated within MathWorks Simulink. Here your plant and controller models are running within MATLAB and also within your host machine, which means that it's purely virtual testing. And next is a software in the loop. Here is where your controller code would be generated. However, this also runs on your host machine, which still interacts with the simulated plan. The key difference from model in the loop test is that you are now verifying the generated code itself. Followed by that, we have a process in the loop. This is a significant step. As you can see in this case, a controller's generated code would now run on the actual targeted embedded processor, while the plant simulation still remains on your PC. So the crucial difference here is that we introduce the real hardware in the loop. And finally, the hardware in the loop test, of course, the last stage, which is mostly a comprehensive test where your controller runs on the final embedded ECU, and even the plant is simulated by a dedicated real-time hardware in the system. This final stage tests the completeness of the system in a very realistic environment. And MathWorks HSP offers the critical link between your Simulink models and the actual embedded hardware. Therefore, we will explore each one of these stages and the role of HSPs in more detail shortly. Let's start with the model in the loop test, which is the most primitive test that we can do as of now. As I told, this would be the first step where everything is simulated in software. Your plant, which is your system you want to control, would be basically a functional model, and your controller would be the application which you are developing. And we do all our initial design and verification within the simulation environment of Simulink, even before generating any code or touching the hardware. All right, I just tried to capture some snippets from MATLAB so that it's easy for today's webinar, so that we need not go back and forth between MATLAB and presentation. So this is how the output looks like. Here's a simple example for model in loop test. Our first objective would be to create a functional model and execute the model in loop simulation within the simulation framework. As you can see on this slide, we have built a functional model which implements a simple voltage to PWM algorithm. We are taking the input here represented as the ADC resolution signal. Perhaps this is just the simulated ADC converter reading, and this ADC resolution is then scaled by the gain block. If I had to make this simple for you guys, as you can see, the function model you guess on top is basically implementing whatever the mathematical formula that we have here for calculating the PWM duty. And the PWM duty output is then sent to a scope block so that we can visualize its behavior. So finally, to execute this model in loop simulation, uh, we simply run the simulation for roughly 10 seconds, and immediately you see the result in the scope, which is plotted at the bottom left. Here, the blue line shows you the ADC resolution input, which is a simple ramping signal increasing over time, which basically simulates the changing ADC value. And the red line above it is our calculated PWM duty cycle. As the ADC resolution increases, which represents a rising input voltage, our PWM duty cycle tends to decreases, which basically demonstrate that we have an inverse relationship between our algorithms, and that was totally expected. And moving to the next objective for today, which would be to configure the hardware. I'll just quickly try to wrap up what's the most important stuff that needs to be touched based on a hardware side. We'll be using the embedded coder app basically to configure the hardware settings for our TC3 board, specifically for the TC375 light kit. First, select the board from the drop-down menu and then make sure to configure or verify the system clocks, which is super critical for time-sensitive peripherals like ADCs and PWM. Next, then check your USB or DAS interface to confirm that the board is properly connected to your host PC. And once that's done, I think we are good to go for the simulation and deployment. Before we get into the actual demo, last couple of slides from my side. The next step that I wanted to explain is all about the process in the loop simulation, where we split the system into two parts, as usual, the plant and the controller. The plant is a system that we want to control. It's basically modeled in Simulink and stays in the simulation environment. However, the controller is our application, which runs on the actual AURIX hardware or a processor simulator in this case. The two parts communicate in real time. Basically, the plant sends feedback and controller sends control signals back. This setup would let us test the real embedded code in an environment, in a realistic environment, even before we fully deploy the code onto the hardware. Now, beyond just simulation, let's briefly take a look into the process in the loop test, how the setup is and how it's done. Our objective is here to verify our generated codes actually has the equivalence for the actual embedded processes behavior, and we use SPIL to confirm that the generated code's behavior is numerically identical to our original model, which is our subsystem in this case. And with the help of SPIL test, we can also perform functional tests with code coverage analysis, and most importantly also do profile code execution to understand the timing behavior on the real hardware. So last slide for today. Our objective is basically to run the application directly on the actual hardware and to show you how it looks like on AURIX TC375 light kit. Maybe let me try to shortly explain this block diagram before I go into the real simulation. On the left, you see a potentiometer which provides the analog input voltage, and this is being captured by the EVDC as a 12-bit digital value. This digital input feeds into our algorithm, which is our controller application running on the Tricore. Then the algorithm's output would drive the LED via the PWM module on the pin header of P000.5. So we basically control the LED's brightness by updating the PWM's duty cycle, which we'll see in a couple of minutes. I would say this setup basically demonstrates a complete hardware application, say starting from reading an analog sensor and being able to process it within our embedded code, and being also able to control an output on the real AURIX hardware itself. I think it's the right time that we jump to the demonstration. I hope by now should be able to see my camera also with the board. This is the TC375 light kit board that I'll use for today's application. Uh, um, to show you guys how we are controlling the LED brightness using the potentiometer. As you can see, this is where the potentiometer knob is, and this would be the LED here that we'll be trying to control. Just a second, let me darken this so as you can see now, it's much more brighter, that your LED is glowing here. Basically, we'll try to control the brightness of this LED by changing the potentiometer knob. And so as you can see here, once I turn the potentiometer knob, now the LED is completely turned off, and I'm now switching it onto the right side. The LED is starting to glow slowly but steadily, and now it's at its maximum brightness. Yeah, which clearly demonstrates that once we turn the potentiometer, the ADC resolution value decreases, thereby reducing the PWM duty cycle, which would in turn reduce the brightness. On the other hand, when we turn the potentiometer to the left, it decreases the ADC resolution value that is being fed to the model, and the PWM duty cycle increases, which of course increases the brightness of the LED. Maybe to have a much more intuitive way, I have a scope connected to the pin header, as I mentioned earlier, so that we can see how the PWM pulse looks like. Let me start the capture. As you can see, this is how the PWM signal looks like, which is being fed to the LED controller. So I'm just side by side having my camera so that you can see what actually happens to this scope diagram when I'm changing the potentiometer values. So as you can see now, I'm increasing the knob, and it basically increases the pulse width here, and when I'm decreasing it, it's also decreasing on the left hand side. Maybe just for intuitiveness, I can also add a measurement here. So let's calculate the positive duty cycle. So you can clearly see what is the duty cycle value here. So duty cycle would basically range from 0 to 100%, and so you can see we are able to bring it to the least possible, around 0%, and then while we increment this, the duty cycle constantly increases, and also the brightness of the LED here. Maybe it's too small to look into, but I could clearly see that the LED's brightness is at its best, and which basically shows our model-based development workflow is actually running on the Infineon targeted hardware, which is our TC375 light kit. Yeah, with that, maybe I give back to Michael for explaining us about the tool qualification and concluding today's webinar.
Okay, thank you, Aranyan. This was a really impressive demonstration how we can do model-based development with MathWorks Simulink and with the underlying SafeTpal drivers for ASIL-D or SIL3. And if we are talking about ASIL-D, SIL3, and such high functional safety related development, we have to talk about tool qualification as well. And for the tool qualification kit is available, and we will not go very deep in this tool qualification kit today, because it would extend the time frame of our webinar. And here I will give you the hint that we will have in November another webinar about SafeThsp, and we will there go deeper in the ISC certification kit, so that you have for your safety critical applications a complete tool chain qualified and tested, and you have all together for final certification of your application. Okay, to summarize up with the SafeTpal suite, we have a suite which supports all relevant standards, which gives you a really time to market opportunity into your project, benefit from our experience, and we help you to save time and money with the SafeTpal package, because you can benefit from our experience, what we have done, and we have ready-to-use solutions for you and your project. Okay, maybe you are curious about what's going on with SafeTpal and with our webinar series. So our webinar series for summer is closed today with Eranjan's presentation, but we will follow up in autumn to go deeper with safety schematic. So the hardware in the safety suite, with the safety hall, going deeper in the drivers, with a special safety development, how we can help you in your development project. And with Safety Hill, the remote solution for making hardware in the loop tests. On the other hand, we are looking forward if you want to visit our booth at the ESE Congress in Sindelfingen. There we will have a session in the Congress about Safety Hall and Safety Hill. And we will be present at the MATLAB Expo 2025 in Munich at the Infineon booth. So I'm looking forward to see you in personal, and we will finalize this webinar series in December with a complete overview over SafeTpal and all the components of that. Okay, I see we have a little bit time left in our webinar, and there were some questions out of the audience. Eranjan, is there a plan to support not only TC3xx but also TC4xx and Traveo, for instance, targets with SafeThsp blocks?
That's a good question. We have been, in fact, internally discussing a lot on this topic. And just to align our focus on SafeTpal product and its roadmap for the longer run, as of today, the short answer is yes. SafeTpal's roadmap would include also the long-term support for TC4xx and Traveo 2 targets. However, extending SafeThsp and Safety Hall to this platform would be a considerable amount of efforts. So our initial focus is on TC3 microcontrollers for MVP, and then followed by TC4. Then we will focus on the other needs based on how the market progresses and based on the customer requests that we get on this topic.
Okay, I think that's a very good solution, and we are going for the market as well. Another question, I think it's very from an expert. How does SafeThsp guarantee deterministic behavior in the context of MathWorks real-time workflows?
Okay, that's more of a classical technical question. Yeah, also the answer to this is this is one of the key constraints that we take into consideration when developing our MathWorks blocks. And whenever it comes to SafeThsp, we would also ensure deterministic behavior by using the hardware time peripherals like the GTM and GPT-12, so that they are all aligned with Simulink's real-time execution model. So there'll be no compromise on the deterministic behavior.
And next question, what's the advantage of using SafeThsp over relying on Infineon's ASIL-D drivers with MathWorks HSP?
Yeah, SafeThsp, as I told, offers a lot of advantages on different aspects. But considering the commercial advantage, as I told earlier, it provides certified and high-level Simulink blocks with built-in safety monitoring and error handling functionalities. While ASIL-Ds, it requires manual efforts for qualification, right? Which basically then shortens the development cycle and therefore reduces the risk possibilities and also simplifies the ASIL compliance within our MathWorks workflows. I think that's pretty much all from my side I can say about.
Okay, and shorting the development cycle is a very important issue because, as all we know, that projects are all running out of time and budget. And if you use safety Paul, the SafeTpal suite, I think you can make your boss happy. Okay,
Absolutely.
Ranjan, thank you for your very interesting presentation and the live demo. Maybe there are some other questions coming up. We will answer them at the end of the webinar. We will send you a link to the recording and to the presentations. And if you have more interest, don't hesitate to contact us directly. Here are our email addresses and our telephone numbers. And on our website, we will find more information about SafeTpal and the other solutions of Hitex. Now it's time to say thank you for your participation in this webinar, and I'm looking forward to hear or to read from you, or I'm looking forward if you will join our other webinars as well. Thank you all and have a nice day and a nice weekend.